Okay, so last time, I discussed conservation laws or integrals, or more precisely integrals of motion. And then I think we ended, so I explained what not explained, but just mentioned basically what a completely integrable system is. I think it's an important topic and we will return to it. It just, right now I want to go through the basics. So in particular, so I want to revisit the variational principle and now formulate the variational principle for the phase space. So variational principle for Hamiltonian mechanics. On the cotangent bundle. So remember we discussed the kind of the degree of degeneracy of the Lagrangian variational principle. The totally non-degenerate system and the ones that we like and we call the Lagrangians, they have the matrix of second derivatives in velocities positive definite. So so that's what should be called non-degenerate Lagrangian principle. But then I mentioned that you can consider another extreme case when the matrix of second derivatives is identically zero, which means that the action is linear in velocities. And then we derived some kind of non-degeneracy principle in this case, and I want to return to this. So I want to formulate the variational principle for Hamiltonian mechanics on T star Q, and you will see that it's very much return to that discussion. So let's consider the space of path. So this will be the space of parametrized path. Now on the phase space, so parameterized path. You know, the difference between parameterized path and non-parameterized path is like the difference between geometry and topology. When you have a non-parameterized path, that's something that belongs to the topology. When you have a parameterized path, that's a dynamical system, that's geometry, and there's way more information there. So now on the space of such maps, define the functional, which is the following. It's an integral over the image of sigma. Now this is a non-parameterized path. It's just the image of this map. And alpha is a one form on T star Q that is locally in local coordinates. Alpha is sum over I, pi dqi. So I just want to emphasize that this term, it's topological. Say, if we would want to formulate topological classical mechanics, the ones that depends only on the topology of path, depends only on the topology of our manifold Q, that would be the object. I mean, this part of the action depends only on the topology of our path. And then the second part, that's what it makes geometric, that's what it makes dynamical system, is the integral from T1 to T2, the Hamiltonian, evaluated along the path. And our parameterized friend is this, from T1 to T2. Okay, so we consider this this functional, and just a small remark. If we will replace T star Q by some symplectic manifold, so replace by a symplectic manifold well, sorry, it's the end of the day. M with symplectic form omega, you can still define such action, but only locally where omega is d alpha. So if you want to have this action globally defined, then you should require that M is an exact symplectic manifold. And then the story is identical. So we will see what to do in case when when M omega is not exact. We will discuss it later. Okay, so as usual with the variational principle, let's first derive the variation. So first variation. Again, if you want to be conceptually mathematical, we have to choose a path in the space of path and differentiate in the tangent direction along this path. And that's what is called variation. If we are okay to be somewhat more intuitive, then we can just do infinitesimally small variation of sigma. And before I will do this, I want to write this action in the equivalent form. So now I'll replace dq restricted to the path by the derivative of q times dt. And so the whole action can be written this way. So now I wrote the first term, which is topological, still using the parameterization. Okay, now it's easy to compute the variation. So if I vary in the cotangent directions, I will have delta pi sum over I, and then q dot I t plus dh dpi dt qt dt. When I vary in q, so I have sum over I pi delta qi dot plus dh dqi. Sorry, this should be upper I. This should be upper I. Everywhere should be upper I. I want to be careful because I know that there is a difference between covariant and contravariant tensors. One is transforming according to the vector representation of SLN when you change coordinates. The other is transforming according to the contragradient representation, the dual representation of the vector representation. So now I can write this. So the first term is just as is, so I will not write it again. So I'll just write the second term as integral from T1 to T2. So now I'm integrating by parts. it will be minus pi dot plus and I forgot here to put delta qi plus dh dqi evaluated at the trajectory delta q it dt, but then when I integrate by parts, I have to take into account the here sum over I. I have to take into account boundary terms. So I have pit delta qit between T1 and T2. So now critical points. And so I varied along the path, and then I want to impose boundary condition because all our problems, they are boundary problems. And boundary conditions means that, say, P T1 QT1, this boundary point of path sigma, I constrained it to L1, some submanifold in T star Q, and the same for P T2 Q T2. I also constrained it to the submanifold L2 in the cotangent bundle. So constraints. So very good. So then critical points. So first, if we want this to be 0 for any variation of P, then so I will just write it like this. Bulk term for the variation in P gives these differential equations, which we are quite familiar with. So dH, why do I have minus? That's correct. No. Yes, because, sorry, I have to change the signs everywhere. Just every sign was wrong here. So it's minus H. That's the correct sign. Okay. So now we have correct sign here. dpi pt qt delta qi. So we have p dot I t equals minus dh dqi pt qt. These are the Euler-Lagrange equations. I mean, the standard terminology, I think it's the bulk terms in the variation, in the sense that this is the where we integrate over dt, and then boundary terms. On the boundary, we have to have this thing that should vanish. So sum over I pit delta qit between T1 and T2 should vanish. But variations delta qi T1 and delta qi T2 are independent, which means that we should have two equations. So I mean, two terms should be identically zero. Restricted to L1, it's zero. So when we vary delta, so I just want to say that delta Q T1, it's the tangent vector to L1 at the point PT1, QT1. And this tangent space is a subspace in the tangent space to our phase space, to T star Q at this point. And similarly, we should have Pi T2 delta Qi T2 at L2 should be equal to 0. So so geometrically, these conditions simply mean the following. So we have alpha form in local coordinates. It's a one form that can be written in local coordinates as Pi dQi. It's one form on T star Q. But now in T star Q, we have this submanifolds Li, the boundary condition submanifolds. Let's denote these embeddings iota sub I. So these are injective mappings to T star Q, kind of tautological mappings. It's a submanifold, so we embed it there. So then what we can do is we can pull back this form alpha to a one form on this submanifold Li. It's pullback or a restriction. It's a restriction in the most natural sense. So that's boundary conditions. They simply say that the pullback of alpha at the point PTA, QTA should be equal to 0. And it simply means that this is a condition not on sigma, but this is a condition on these submanifolds. No, sorry, it's just this is what it is. That is 0. So that guarantees this. Guarantees that boundary terms vanish. Okay, so let's think about these conditions. So these conditions, let's say that we have dimension L1 conditions on one end and dimension L2 conditions on the other end. If we want to have optimal number of conditions, we have 2n differential equations. For 2n unknowns. According to the general theory of differential equations, the optimal number of boundary conditions is 2n. So then we can hope, in this case, if L1, L2 are generic, we can expect finitely many solutions. not necessarily unique solution. That would be ideal, but typically finitely many solutions. If they are sufficiently generic, and that's the definition of generic, more or less. So now let's look at this condition and on this condition. So it's, it's a basic fact from geometry that pullbacks commute with the Ram differentials. In other words, d of this is equal to pullback of d alpha, but we know that d alpha is omega, and we know that this is 0, which means that the restriction of the form omega to our submanifolds should be 0, or the pullback should be 0. So what kind of submanifolds are these? We had a special name for that. In symplectic manifolds, we identified 3 types of submanifolds.
The Lagrangian submanifold.
Hmm?
The Lagrangian.
If we just want this, it's a little bit less than Lagrangian. It's isotropic. So meaning that these are isotropic submanifolds. And what do we know about isotropic submanifolds? That the dimension of Li is less or equal than M. But we have this condition. If we combine this together, we see that you're absolutely right, they should be Lagrangian. If we want both of these. So the conclusion boundary conditions, let's call them variational boundary conditions, when the variation is vanishing entirely, including boundary terms. Boundary conditions are, we also have this special condition, this one. So let's call this alpha exact Lagrangian submanifolds. Alpha exact is identical to the fact that this pullback alpha is 0. So this is the main conclusion. For the time being. And now let's return to the fact that we have finitely many solutions when they are Lagrangian, when the dimension of each of them is m. And let's see a good geometric reason for this. So let's call this 1. This was the analysis of boundary conditions. And 2, the analysis of Euler-Lagrange equations. So let's assume that T2 minus T1 is small. so that for each initial condition P1, Q1, there exists unique trajectory PT, QT when T is from T1 to T2. Let's call it sigma C. So let's denote this. So that means that yes. So let's say that L T1 T2, it's a submanifold in TQ cross TQ that consists of points P T1 Q1 QT1 in the first copy, sorry, and P T2 Q2 in the second copy, and there is a path connecting them, sigma critical. That is a solution to the Euler-Lagrange equations. So we can just say that this is a submanifold of solutions to the Euler-Lagrange equations between the time T1 and time T2. Theorem, that's a very nice homework. L T1 T2 under all these conditions, if we consider it as a submanifold, when we take minus omega 1 in the first copy corresponding T1, it's a symplectic manifold with the negative symplectic form. It doesn't matter what the sign of the symplectic form is. It's still closed, non-degenerate two form. So is a Lagrangian submanifold. I mean, it's clear from the general theory of ODEs, from Picard theorem, that it will have the dimension 2n, which is half of the dimension of this thing. Lagrange, for the Lagrangian submanifold for this symplectic structure. So the only thing to show is that this submanifold is isotropic if you consider omega minus omega as the symplectic structure. Isotropic in this product of the symplectic manifold, and product of symplectic manifolds is a symplectic manifold. It has natural structure of the symplectic manifold. Okay, so now you see we have proof, homework, the dimension is 2n is obvious. So you really have to prove that LT1, T2 is isotropic. And that's a simple fact that follows from the Euler-Lagrange equations. But now, as a consequence, we have two Lagrangian submanifolds, L1 here and L2 here. And as a result, we have in this product, we have L1 cross L2. So we have two Lagrangian submanifolds, this one and this one. Each of them has dimension 2n, and the total dimension here is 4n. And that's a general fact that if L1, L2 are generic, there exist finitely many intersection points. LT1, T2, intersection L1 and L2. And these finitely many points, they are in bijection with solutions to Euler-Lagrange equations with boundary conditions L1 and L2. And so that's a geometric meaning, if you want, of the fact that that I mentioned before about 2n constraints on a system of 2n differential equations of first order. So I don't know, any questions about this part? So now we will see that this is not enough. We will see that we need a little bit more structure.
Yeah, is the sign important for the negative omega?
Yes. Otherwise, it will not be Lagrangian.
Okay. Okay.
I mean, otherwise it will not be isotropic. It's what you need is you take this symplectic structure omega comma minus omega, and then you pull back this form to the product L1 cross L2,
Okay, and then crosses zero.
and then it should vanish. And with the minus sign, it vanishes.
Okay, thanks.
Any other questions? Okay, so now let's consider the time evolution. So now composition of solutions to Euler-Lagrange equations. Okay, so now suppose that we have a Lagrangian L1, Lagrangian submanifold in our phase space, Lagrangian submanifold L2, and some Lagrangian submanifold L3. So we have, so this is at time t1, this is at time t2, and this is at time t3. And suppose that we're in the nicest possible situation when there is exactly one trajectory. So that's exactly one trajectory, sigma classical, connecting L1 and L2 in time t1, in time t2 minus t1. So that's the unique solution.
I'm sorry, just to check. I can understand how genericity or genericness will give discrete collection
Yes.
of intersection points, but why is it finite?
Well, this is sort of more, even more about generic.
Okay.
I mean, yes,
So
typically you just get the discrete number, but if you vary them sufficiently carefully,
Okay.
then you can gain finitely many intersection points.
Okay. All right. Thanks.
I think there is a theorem like this. If not,
Okay.
for all our purposes, discrete is enough.
Yeah.
So then somewhere here, let's assume that L2 and L3, again, the nicest possible situation when there is another, let's call this sigma 1. So then this is the unique solution, again, unique solution to the Euler-Lagrange equation with boundary conditions L2, L3 in time T2, T3. But the problem is that everything is completely determined by the choice of L1, L2 in the first case and L2 and L3 in the other case. So the initial and the target positions will be completely determined by the equations and by the choice of these Lagrangian submanifolds. So there's absolutely no guarantee that this path will be continuous. So in order to sort of join these two paths, we have to move around this L2 in such a way that these 2 points, they become one. So the conclusion is that typically the path connecting L1 and L3 through these piecewise solutions to the Euler-Lagrange equations is discontinuous. Connecting L1, L2, and L3, which is not good. So let's make it continuous. In order to make it continuous, we should be able to vary L2. And vary, well, if we want to vary L2, I mean, we shouldn't say when we're deforming L2, this deformed L2 better not to intersect the undeformed one. In other words, we have to have a picture something like this. They shouldn't intersect. In other words, we have to have fibration. So, which means typical fibers. So, typical fibers do not intersect. So then, if we vary L2 along this fibration, sooner or later we will hit the situation when there will be at least one continuous path connecting L1 and L3 through L2. Maybe there will be several, but one is enough. And so the conclusion is that if we want to compose solutions to Euler-Lagrange equations, and we definitely want to do this, our boundary conditions should not be just Lagrangian submanifolds. They should be Lagrangian submanifolds which are part of the Lagrangian fibration. So boundary conditions should be Lagrangian fibrations. An example, suppose that you have an integrable system. So suppose that you have n independent functions on the cotangent bundle to our configuration space, such that, so independent means that, okay, here is the geometrical way to say what it means to be independent. It means that this form, this differential form, is not zero identically. It can vanish at some singular points, but it shouldn't be zero identically. Such that they Poisson commute between each other. So then level surfaces MC, so the points where we fixed the value of these functions, are Lagrangian fibrations, Lagrangian submanifolds, and they are fibers of the Lagrangian fibration, where this is a subset in Rn, and Bn is just the points of all possible values of I. So it's a point of all possible values. And typical fiber will be Lagrangian submanifold. There will be some singular level surfaces where the fiber will not be Lagrangian, but on the subset of they will be measure zero. Okay, so this is the conclusion, and we will see this. We will see how it will be working in quantum mechanics, where basically these Lagrangian fibrations will define spaces of states in quantum mechanics. So one way to construct the quantum mechanical system through the geometric quantization uses these Lagrangian fibrations as so-called real polarizations, and that's the way how one can construct spaces of states in quantum mechanical systems. Okay, so this is the main conclusion, that if you take into account that sooner or later you will have to kind of consider compositions of solutions to Lagrange equations, then inevitable the correct notion of boundary condition should be Lagrangian fibration. Any questions about this?
I guess, I mean, so in this process of varying L2 to get a solution that, from L1 to L2 and L2 to L3, so that matches up, I assume that you could get multiple solutions depending on how you vary,
yes,
right?
yes. Definitely.
So how does that feed into the notion of composing solutions?
Into notion
I mean,
of,
does it still make sense to say that we're composing solutions when
yes, why not? So for example, you might have something like this. Say two solutions connecting. Sorry, I shouldn't write it like this. So you have two solutions connecting L1 and L3, and then if you choose L2 in such a way that it intersects these two trajectories, then you can say that each of these solutions is a composition of two solutions. So basically, the idea of the correct composition is that first you solve the Euler-Lagrange equation for the interval T1, T3.
Mhm.
So then you know the possible results of the composition. And then you can see which Lagrangian fibers
Oh.
will intersect those trajectories.
Okay. Okay.
Clearly not all of them.
Mhm.
I mean, this is a two-dimensional picture, so here it doesn't matter how you choose this curve. I mean, unless it's totally random choice, it will intersect these lines.
Mhm.
No, actually, even in this case, you can choose something like this. This is a Lagrangian. 2D. And it will miss these points altogether.
Mm.
Okay. Did I answer this?
I think partially, but I think my question is sort of like it seems like we can't just specify sigma 1, sigma 2, and then say what is their composition. We need to introduce additional information like I don't know, maybe pi1 of the space of L2s or something like that.
Yes, possibly. What I want to say is that we definitely have to be able to vary L2. Without this possibility, we just cannot compose the trajectories.
Okay.
So that's, I don't know. I hope it's convincing.
I mean, I'll keep. We should just keep going, and then at some point, like I'll see what we're trying to do, and
Okay,
yeah, it'll be
and
important.
we can discuss it.
Okay, thanks.
Mhm. Okay, so very good. So then, last point. What if M is not exact? So in other words, we have a pair where we have a symplectic form, but this symplectic form is not equal to d alpha, where alpha is a one form.
Oh, by the way,
Uh-huh.
when we're taking this collection of level surfaces for the fibers, do we want to remove the non-generic fibers, or do we want to keep them as well? By non-generic, I mean like
Yeah, I understand. I mean, if we remove them, that will make Bn a little bit more complicated.
yeah.
If we don't remove them, that will make the total space a little bit more complicated.
Yeah, and
What we really want to do is we want to vary our fibers when we vary the base point on a good subset in Bn.
okay.
And when we do this, they remain Lagrangian. And what happened at singular points? I guess it's actually important, but for different reasons. You may have some interesting monodromies if these are singular points. It's actually the theory of Lagrangian fibrations on symplectic manifolds. It's interesting even from this purely applied sort of point of view of studying integrable systems. So, but for our purposes, we can do either. I mean, I think your proposition is probably the best. Just remove all the singular points, and when we vary C in this case, we just go along the good part of the
Yeah.
of the base.
Okay.
Okay.
Yep. Thanks.
Right. So now what happens if it's not exact? Well, in this case, so if not, so in this case, still there exists a connection sorry, there exists a line bundle over M. Let's call it E. It's the total space of the bundle, and these are the fibers. And the connection alpha on E, such that omega d alpha is the curvature of this connection. So that always exists. If E is trivial, in other words, it's R cross M, then a connection becomes one form, and we have the and that's when M can be exact. So what is so this is the so this is the general set. This line bundle and a connection on it such that omega is the curvature of alpha. So E is called the, or rather, a prequantization line bundle. So usually this prequantization line bundle is a circle, and then there are some integrality conditions, so we don't do this. So for us, it's just really a real line. And then in this case, we can still write the action as the integral along the image of sigma, connection alpha, but now this integral has a different meaning. This is the holonomy of alpha along this non-parameterized path, minus the integral t1, t2, and then it's the same, dt. So this thing is not a function. It is a section of well, it's a section of E over the target point and the source point of sigma. So I don't want to do this in details because I think we will never come to this point in the quantum case. I just want to let you know that the exactness of the symplectic manifolds is not really important here. So you can modify the notion, and so in this case, that will be the action function. but then, you know, these sections of E, they may still have critical points. Then you can do variation in exactly the same fashion. You will still have differential equations. You will still have the same structure of boundary conditions. They should be Lagrangian fibrations. Everything is parallel, except the action itself is not a function anymore. It's a section of this line bundle. Okay. So since I was very brief here, I'm not going to ask if there are any questions. I hope there are no questions. So now the last subject in classical mechanics are states. So classical mechanics is deterministic, but we all know that Newtonian mechanics is, and you know, the whole notion of classical mechanics, it's an abstraction that works quite nicely in some models, but in real life you have everything is stochastic, everything is probabilistic. So here's the definition of a state. So a state, probabilistic state, on the phase space M is a probability measure on the phase space. So examples. So first, a state supported at the point x0, deterministic state. So if you have a subset in M, the measure of this subset is 1 if x0 belongs to you and 0 otherwise. So if you want to integrate a function with respect to this measure, this is simply f of x0. So we can say that this is the Dirac delta function, or delta distribution, supported at x0. Another example, suppose that we have a submanifold and we can have a probability measure supported on N. So it's the same thing. So we have to, so then we fix probability distribution on N, and if we have U in M, then the measure of this thing is equal to mu, sorry, mu n u, and if right, so we can just say that we have this tautological mapping embedding of n in M, and we can just say that this is the pullback of the measure mu measure nu from n to m. So anyway, so it's too many words, but it's clear what this is. And then finally, a state with the density function, with the density rho. And I want to say the density function rho is the following: mu of u is integral over u rho, and then remember that our manifold is symplectic manifold. So if we will take the symplectic form to the power n, this is going to be 2n form. So it's a volume form. We can use it to integrate, and depending on whether our manifold is oriented or not, we will just take not the form but the corresponding density of the form, and then we integrate this positive function, density function, with respect to this density, and so that's a probability measure, normalization. We assume we must do this normalization, integral over the whole m, rho omega to the n should be equal to 1. The total probability is 1. Okay, so rho is non-negative, and the total probability is 1. So then expectation value. The expectation value here is, okay. So then the expectation value of an observable. Before I will say this, I should say what is an observable. Definition. Maybe I already gave this definition. Say I'm talking about C infinity functions, but sometimes you have to be more specific about which space of functions to consider. Let's just not pay attention to this for the time being. So, because it really depends on the situation. So C infinity M is the algebra of classical observables for the Hamiltonian system on M. So the expectation value of an observable on a state I'll just denote it well. Okay, let's there are two notations. There is physical and mathematical notation. So this is the mathematical notation. So that's the integral over m f with respect to this measure nu. And physical observable is this. It's the same thing. Physical notations. So so then you see in the first example, the expectation value was just the value of function at this point, x0. In the second example, the expectation value of an observable is just you integrate over M, F restricted to N with respect to nu. And in this example, the expectation value is just integral over M, F rho omega to the M. So these are three examples. And finally, the evolution. The evolution of states. So by definition, if you have an observable F, the evolution of the state is the same as you take the evolution of the observable and take the expectation value with respect to the state at the initial point. So, for example, if this is the integral of f of x rho x omega to the n, so then theorem rho t is a solution to the differential equation d rho dt is equal to minus the Poisson bracket of the Hamiltonian with rho, with the initial condition rho 0 is rho. Recall that for if f is an observable, the evolution of observable is defined as f of xt, where x is a solution to the Euler-Lagrange equation with the initial condition x. And then it satisfies this differential, the same differential equation, only with the plus sign. And f0 is equal to f, the initial condition. So this is the kind of formal difference between densities of states and observables. They evolve sort of with different signs. And as a result, you have this identity. So this is a very formal overview of classical Hamiltonian mechanics. And more or less finished the subject. So if there are any questions, I will be very happy to answer them at this point. And then after this, we can move on to quantum mechanics.
Can you give a sort of hint, almost like a spoiler of what sort of things we might want to change or tweak when we start looking at quantum stuff?
Okay, so that's a good point. So let's make a summary. And let's focus on the Hamiltonian part of the story. So we have a phase space. we have flow lines of our Hamiltonian vector field generated by H. These are our trajectories. Solutions to the Euler-Lagrange equations for the Hamilton-Jacobi action. I forgot to give a name. The action, this in the Hamiltonian framework is called Hamilton-Jacobi action. So then we have boundary conditions. Which we know why we will choose as Lagrangian fibrations. On our symplectic manifold M. And then finally we have observables. C infinity M. We know that there is a Poisson bracket for them, so these are elements of the Poisson algebra, of this particular Poisson algebra. And then we know that there are states. These are probability measures on M. And then we know how observables and states evolve. So now in quantum mechanics, well, quantum mechanics is something that, emerged from experiments, from various thinking about experiments, how the constructing mathematical models for experiments. So what I'm going to explain is a mathematical summary of all these very long phenomenological process. And I should say here is the summary of Hamiltonian classical mechanics. And in quantum mechanics, mathematical structures are completely parallel to the classical one, except they start from here. So
Sorry,
yeah.
Before we go there, I just want to check something. So for the third point of trajectories is equivalent to solutions to EL for, Euler-Lagrange for Hamilton-Jacobi action. Is the statement that trajectories are solutions to Euler-Lagrange and they are critical points for the.
Yes.
Okay, all right, thanks.
Yes,
And the
exactly.
Hamilton.
So this flow lines.
Yeah.
They're identical to trajectories, and
Okay.
they are critical points for the Hamilton-Jacobi action. I want to distinguish solutions to Euler-Lagrange equations and critical points, because solutions to the Euler-Lagrange equations means that the variation, the bulk part of the variation is zero. Kind of complete critical point is when the bulk term is zero and the boundary term is zero. And this part is taking care of the boundary terms.
Okay.
So this Hamiltonian is something that defines the evolution, and then whatever we have here, in some sense, this is an algebraic structure of the Hamiltonian framework, or rather, in this case, it's a geometrical and rather geometrical structure of the framework. So in quantum mechanics, this Lagrangian, so let me say that this is 1, 2, 3, 4. So instead of boundary conditions that are Lagrangian vibrations, they are replaced by the space of sections. So this is the geometric kind of Lagrangian vibrations is a geometric counterpart to the Hilbert space. For our quantum mechanical system. And the precise statement is the following. So here we have the Lagrangian vibration. And yes, and this Hilbert space, so geometric quantization construction of H, it tells us that H should be the space of sorry, we have two things. So here we also have this pre-quantization line bound. I'm sorry. So here we have the pre-quantization line bundle, the one that I was talking about. If so, fibers are R. Say if alpha, so alpha is a connection, and omega is d alpha. It's the curvature of alpha. And what you can do is you can consider I will lie now, but otherwise I will have to explain what geometric quantization is. So this is the space of horizontal sections of E well, this is wrong, but I'll say it anyway. So of E with respect to covariant derivatives with alpha. So anyway, so these two structures are counterparts, Lagrangian vibrations and Hilbert spaces in quantum mechanics. Second, so we have classical observables with Poisson bracket. Here, Poisson algebras. Quantum counterpart is quantum observables. Which are associative algebras. Acting on H. So H is a representation of the quantum algebra of observables. And this algebra is a deformation, quantization of this Poisson algebra, in a sense that you can think of this as an associative product on the complexified C infinity on M of M. That starts with the pointwise product. And then the next term is IH over 2 times the Poisson bracket of f and g, and then high order terms. It's very easy to see that associativity, so associativity of this star product in order O of h squared gives the Jacobi identity for this Poisson bracket. So that's a counterpart of the algebra of observables.
I got a question.
Yeah.
So the Lagrangian fibration is like the boundary condition part of classical mechanics,
Yes.
but the Hilbert space is like the Hilbert space of states, right?
Yes.
Like how does that correspond?
Because it's the Hilbert space. I didn't, you see, I said it, but I never wrote that it's a Hilbert space of states. I'm going to say what a state now.
I mean, is there something like should it be something bulk in the classical side
No,
to
no, no.
correspond to the Hilbert space?
I understood the question.
Okay.
Give me a little bit of time, and
Okay.
we'll. So then the Hamiltonian. So it's quantum Hamiltonian. So this quantum Hamiltonian is an operator. So it's an element. Sorry, it's an element of this of the quantum algebra of observables. So it acts on our Hilbert space, and it defines the evolution. So maybe I should define the evolution. Evolution of vectors in H is V goes to, I think it's like this, where H bar is this quantization parameter. Evolution of observables, it's F goes to, you take the conjugation with respect to this evolution operator. And okay, so since you asked this question about the Hilbert space, so I want to say the following, that on M, we can have two Lagrangian fibrations. So this corresponds to the fact that we have two corresponding Hilbert spaces. And so if these two fibrations are related by some kind of symplectomorphism, so then here there is a linear map quantizing this symplectomorphism from H1 to H2. And in this sense, there is no canonical choice of the Hilbert space. It depends on how you want to represent your algebra of quantum observables. The canonical thing is the algebra of quantum observables. Now, why H1 and H2 should be considered as boundary, are related to boundary conditions, simply because roughly speaking, because such unitary operator we also can consider as topological evolution. So we can consider this as a quantum version of the evolution with zero Hamiltonian. This is Hamiltonian. Too many H's. Remember, I was explaining that in the action, in the Hamilton-Jacobi action, you have the topological part and the dynamical part. So it's the topological part that has the derivatives in time. So it's when we vary the topological part, then we gain the bulk terms. So in fact, this is absolutely, I mean, this is a correct statement. I just have to spend a lot of time explaining why it's correct. But it's really true that these linear mappings from one Hilbert space to the other, they are quantizations of the symplectomorphism connecting two different vibrations if these two Hilbert spaces are obtained through the geometric quantization using these vibrations. And hopefully we will have time to discuss this in depth.
Thank you. Yeah.
But that's the idea. Okay, now, so now we have the Hilbert spaces, and you know, I want to argue that by their nature, the Hilbert space has less to do with states, but has more to do with boundary conditions. So then we have the quantum algebra of observables, and we have the quantum evolution, and then finally states. So states are probabilistic linear functionals on the quantum algebra of observables. I probably should give a name to this. I'll call them AH. So in other words, state is just the linear map, which is positive in the sense that it's non-negative. This is zero if and only if a star is zero. Star is the Hermitian conjugate. I mean, one should assume that it exists. And L of 1 is 1. That is what should be called a state in quantum mechanics. So if our algebra is represented in the Hilbert space H, then we can introduce the density operator, density matrix. And then there is a corresponding theorem saying that under certain conditions this density matrix exists, and then this is simply the trace of rho A. And of course, the condition on rho is that it should be non-negative operator such that trace rho is equal to 1. So these are the states, and pure states, these are the states where rho is a one-dimensional projector, orthogonal projector. So And then the space of pure states can be identified with this. This is the Hilbert space. Quotient over the action of the circle, because you know, if you write this as a one-dimensional projector, what is this? This is X tensor the covector. So you first project to this is the projection to X, and you can change X to the e to the I alpha, and that's the action of a circle on our Hilbert space. And so the correct statement is, it's not the Hilbert space, it's the space of states. It's the quotient over the circle. And the reason for this is that the correct notion of pure states is just one-dimensional projectors. Okay, so we dealt with the states. And then what else? Ah, yes, and we already know how to. So number 4. That's the number 4. And the states they evolve. The density matrices they evolve in different direction. This is H T over H rho minus H T over H. Oh, plus. So this is really the quantum version of this opposite evolution. You see here it's conjugation in one direction, and here it's the conjugation in the other direction. Okay, so this is what we will be discussing. And of course, this is a general algebraic framework, but then there are some interesting realistic examples, like hydrogen atom, like the when, say, your mechanical system on T star of the configuration space is quantized, then the corresponding operators are differential operators on Q, Schrödinger operator. So then there are interesting spectral problems, and then there is an interesting question is, say, now you have this operator, the evolution operator. Let's call this UT. So what is the, not limit, but the asymptotical behavior of this operator as H goes to 0? And that's a very interesting question. This is where we will see again all the ingredients of the Hamiltonian geometry that we discussed so far. Okay, I think it's time to finish today. So next time, quantum mechanics. Any questions?
And at the very beginning, you said that topological term. So you mean if it's a homologically trivial circle and integration over alpha is 0, is that what you mean by topology? Like you integrate alpha over.
No, you see, I'm a very naive man. So
Okay.
topology to me is the something that where there is no geometry, where you forget about geometry. So
You mean at the very beginning.
yes, here. So here what I mean is that in this term, there is no parameterization. You can write this term only using the information that is given by this one form, the manifold itself, and a non-parameterized path that's a one-dimensional submanifold in our manifold. in our phase space. That's what I mean topological.
Okay. All right.
It's-
Thank you.
Yeah, really, it's just this.
Yeah.
The thing is that, you see, if you continuously deform sigma, is it correct? No, that's not correct. If you continuously deform, you will get something. So it's not
Is it-
maybe completely topological, but at least it doesn't depend on the parameterization of the path.
Okay.
That's what I mean.
All right. Thank you.
Okay, welcome. Any other questions?
I wanted to know if it's obvious that this action is well defined in the sense of like we probably have a lot of choices for alpha, and
Oh, this action, this is the very special action. It's called Hamilton-Jacobi action.
mhm.
It is especially defined for this very specific alpha.
Yeah, but I mean like if you change coordinates for p and so
Yes. Yes, this is in local coordinates.
yeah, okay.
If you change coordinates, this integral remain the same,
mhm,
because you see we have lower and upper indices,
mhm,
and as you change coordinates, the coordinate transformation, you know, it
mhm.
will be
Okay.
matrix acting on the lower indices and the inverse matrix acting on the upper indices.
Okay.
It's just this mantra of coordinate transformations written explicitly.
Right, right. Okay, okay, I see. Okay, okay.
So that's a very important thing. So then, you know, there are all sorts of interesting generalizations of classical mechanics. You can consider, you know, classical mechanics and supermanifolds, all sorts of derived classical mechanics. When you, I think I think I better not to talk about this. It's scary business. You see, for me, it's almost night time, so I don't want to think about it. For many of us, it's the same time. Okay, so then I'll see you next time.
All right.
Yeah.
Thanks.
Yeah.
See you.
Bye bye.
Thank
Bye.
you.
Mhm.
Bye.